Good afternoon, everybody. It's Tuesday here at TPH, and this one is so good I put on a tie. Like all of you, ties don't fit as comfortably as they used to, but we have been pursuing a discussion with the Salk Harnessing Plants Initiative team for a while, and we are delighted to have them here with us. I won't do a full introduction now, but I will tell you, this team is going to make you think outside the box about what could happen, the art of the possible, and all of the fantastic scientific things going on in our world. So I'll just do a big wave. Welcome, Salk HPI team. We're delighted to have you guys and so honored that you're with us today. All right. Well, we've got some tidbits to go through that are quite exciting because there's a lot going on. Mike Bradley, why don't we start with you? Today was an auspicious one-year anniversary of a big negative price. What do you got on the screen, and what's the attitude going into earnings season?
Yeah, Maynard, it's it's a pretty ugly day today. We read across the screen. It's kind of a trifecta of the market being down, crude oil being down, and just general pulling money off the market because people are just uncertain what's going on right now. You mentioned it right. Last year, this is a one-year anniversary of crude oil hitting almost negative $40. And so at $62, we've come a long, long way in a year. That's a $100 move in a year. Incredible. I'd say what we're dealing with right now is, energy is decoupling. Energy equities are decoupling from crude oil. And I think the reason that is because some of the stuff that we talked about recently about the inflationary trade, that's kind of gone a little bit to the wait side now because the 10-year has come down a little bit here. I also think you're entering Q1 earnings season starting with Halliburton and Baker tomorrow. And I think the messaging, people are uncertain of the messaging, especially when you have a tape that's a little heavy right now. And so I just think, right now investors, with a lot of COVID cases starting to, resurface, both in the U.S. and globally, I think a lot of people are just saying, you know what, I'm in no rush to put any exposure on right now. You've got a market, overall market that's a little heavy. And so that's where we are right now. I fully expect when you hear Q1 earnings tomorrow for the service companies are going to be exactly like you heard in Q4, probably a little bit better on activity, probably nothing good on the pricing side, but, earnings are going to be okay. And you're going to hear that, their E&P guy, the guys that supply the E&P companies, they're really not going to be picking up rigs dramatically. They're going to be maintaining capital discipline. And so it's just going to be more of the same. And that's not a bad thing. That's a good thing.
All right, Mike. Well, next week.
One last thing I'd say, too, is, April 28th is next Thursday. We have another OPEC meeting. People are now starting to think about that now. What's the messaging going to be out of that, especially given they were taken aback by the increased message just a little over 3 weeks ago.
All right, well, I was going to say, Mike, next Tuesday, we'll be saying you're 2 days away from OPEC. What's the chatter? And also tell us about all these earnings we've been hearing. So thanks, Mike. Let me jump to you, Matt. I know you had some news on our theme today, a little bit about sequestration, some up north and some related to tax down here. So what do you got?
Sure thing, Maynard. The Canadian E&P team was actually quite busy today. We put a little bit of color in the note on two bills that are being potentially looked at. Well, one is a bill and one is a potential change from the federal government. On the federal government side, it does look like Canada is looking to potentially move towards a tax credit system, or at least get some feedback on a tax credit system that would potentially incentivize CCS development. But importantly, it would not include EOR in that conversation. However, on the same discussion point, we are seeing a bill being proposed, Bill 262, which actually could look fairly similar to the 45Q credit we have in the U.S. that would actually benefit the industry in being able to use CCS and EOR development and oil recovery development. So both of those things are driving a lot of interest from clients in the Canadian market. And then yesterday in the afternoon, there was some news out that there are a couple of congressmen on the Republican side that are potentially looking to enhance the 45Q credit in the U.S. This would come in a couple of different ways. First and foremost, it would be a potential permanent extension of the credit, which would be very favorable. But as importantly, it could potentially increase the credit itself. So currently, If you use CCS for oil recovery, you get about $35 a ton, and that would be potentially increased to $50 per ton. And then if you aren't using it for oil recovery, currently you get about $50 a ton, and that could increase to $80 a ton. I think for us, the takeaway is that if you continue to see legislation pushed into the market of that nature, it will be very helpful to get these projects off the ground. A lot of this technology starts to really work quite well in that price range, and it could be a big benefit to the market overall in terms of carbon reduction, but also something that will be really interesting for the upstream industry and potentially being able to participate, as well as some of the midstream and downstream players as well. So something to keep on everyone's radar screen, and it is clearly very topical with investors today.
Matt, we're going to have to track those Congress people down and get them on the show and see how we can help them. That sounds like pretty good legislation. Craig Webster, you had some ESG news you were talking about this week. What do you got?
So Equinor announced that they were going to, starting in 2022, be putting their energy transition report to a voluntary shareholder advisory vote. And it was notable because Shell did the same thing, although they're doing theirs this year. They put out a new energy transition report, and they're going to be putting it to a non-binding vote to shareholders in May of this year. And so it'll be interesting to see what shareholders have to say. It is an interesting aside that Equinor actually has a shareholder resolution before them that they're advising shareholders to vote against, asking for intermediate targets on scope 1, 2, and 3 emissions. So it's not like everybody's going to be satisfied, but this is the kind of thing that we see more in the future.
It's a pretty fascinating exercise to lay out a plan and then ask for is it a non-binding vote, you said? So it's a bit of, I don't know. Are you think we're going to see more of this?
Yeah, I think so. I mean, I think, there's sort of a bit of an arms race to see who can, who can set the highest standard, I think, for transparency around ESG. And so it would surprise me if we didn't see more of it. It is non-binding. It's sort of like say on pay. But even though it's non-binding, it is guiding. And we have seen that with say on pay, that it's something that the board hears and there's reaction to. So I would expect to see more of it for sure.
Okay. Thanks, Craig. We've also got Bobby Tudor with us today. Everybody knows Bobby is the man who needs no introduction, at least around TPH. But Bobby's been doing a ton of work with the Greater Houston Partnership, and in particular has been leading the GHP's efforts on transition. And Bobby, there was a lot of news in the last 24 hours, so we wanted to grab you and let you tell our viewers all about it.
Great. Thanks, Maynard. It's been a very big day, if you will, in the world of energy transition, and in particular for our region here in Greater Houston. ExxonMobil announced yesterday evening their intention to lead a consortium to build the largest CCUS project in the world. Estimates here in size kind of range up to $100 billion in size. So to give people some perspective there, ExxonMobil's total CapEx in any given year is about, call it $35 billion. So a $100 billion project is a very big project. That capital, of course, won't all come from ExxonMobil, and it's expected actually that the project ultimately will require very, very sizable government support to get it off the ground. But the whole idea is that you go to the Houston Ship Channel, which many of you may not know is the largest contiguous industrial complex in the world, and is full of petrochemical, chemical, and other industrial companies, many of which are quite large emitters. They're processors of hydrocarbons, generally speaking. And the idea is to get those ship channel-based industrial companies to join into this, to ultimately kind of contribute their CO2 emissions, if you will, to a joint project of gathering those emissions and then shipping them via newly constructed CO2 pipeline to offshore reservoirs where they would be stored. This is really, really big news, because, number one, because of the scale. Number two, because of the number of companies that will be required to participate for the whole thing to work. Number three, for us in Houston, because it's happening here, our view has been generally that large carbon capture sequestration projects really should happen in large industrial complexes. Industrial emissions account for about a third of all CO2 emissions globally. And so going after them at the kind of scalable source point, if you will, of major industrial complexes like the Houston Ship Channel seems a very, very sensible thing to do. And we're very pleased to see Exxon show real leadership on this, jump on it, if you will, and help drive it to fruition. So this is very big news in the world of energy transition. And if we can get this accomplished, it'll undoubtedly take a lot of time, a lot of policy help, a lot of technological evolution. But Exxon clearly believes that the pieces are in place to get this going, and they're getting after it. And it's really great news for Houston and great news for the world. I think our view would be that there is no path to being on track with Paris climate goals in the near to intermediate term without major progress in CCUS. And this is what it's going to take. And so this is a great project to get it going.
Well, it's really exciting, Bobby. Thanks. All of us appreciate your efforts and you keeping us posted. It's almost like the concept of, if we're going to really effectively capture CO2, we have to have these concentrations of places where it's produced so that we can efficiently do it. So it makes you think over time, it'll almost be like global zoning. Like, let's put all the industrial stuff here and stop scattering things around. But anyway, your comments on the Houston Ship Channel, I don't think any of us realize how big and powerful and impactful just that piece of real estate is.
Yeah.
Thank you, Bobby. Well, Colin, you've heard the tour here, which is, it is Carbon Sequestration Day, big time at TPH. What have you got for us?
Well, it's one of my favorite topics, so I'm really excited to get to the meat. But we have a couple of slides prepared on context, and so I thought these might be useful. Back to the point of the sub-zero price for crude oil 1 year ago, this $100 price advance over the past 12 months is actually the largest advance in the history of the oil market. You can see there the next 9 largest moves all took place in June and July of 2008 at the height of that famous oil price spike. And they were in the tune of $70 to $74, coming off a starting point, that was roughly the same. The highest price year to date has been $67.98. That was achieved on March 8th. And I think part of what we're seeing is that big move in the price of petroleum liquids is beginning to hit the real economy. And so, for example, in just the past couple of weeks, we've had 2 major consumer product companies announce that they're raising wholesale prices on consumer goods such as diapers, toiletries, and so on. And that clearly is part of the reason that equity markets are responding. Turning over to CO2 emissions, these are charts that show you U.S. energy-related CO2 emissions from 1965 to 2019. The news flow is telling us that the Biden administration may, on Thursday, announce a nationally defined contribution target of 50% of U.S. emissions as of 2005. So there, the relevant thing to know is that energy-related CO2 emissions, which is about 75% of total, were 5.9 gigatons in 2005, 5 gigatons in 2019. Notice that that's a little bit less than 30 years prior in 1989. And if we were to have the 2005 number, we'd be to about 2.937 gigatons in 2030. Now, if you look at the 2019 numbers relative to that 2005 level, you can see the United States is already down 15%. That's comparable to the success of Japan, Germany, Switzerland. It's a little bit better than Norway and Belgium, but it's the United Kingdom that really stands out as being ahead of the rest of the pack. And then, of course, a number of countries are moving in the wrong direction. If we look at the 30 largest emitters in 2019, China was the largest at the national level, about 29% share of total. US was number 2 at 15. A point that you've made before, Maynard, 65% of emissions come from the non-OECD economies, 35 from the OECD economies. So really, everybody has got to pitch in. And as Bobby just said, carbon capture is clearly essential. We have to have carbon capture. And then this is the cumulative energy-related CO2 emissions, 1965 to 2019. Even though China is the largest emitter as of a point in time today, the cumulative emissions have the United States still as the largest emitter over that time horizon, 274 gigatons. Europe is number 2 at 256. China, unfortunately, is rapidly catching up, 208. On current trends, China would become the largest cumulative emitter by the year 2034. And you can see India is down here. And in the pie chart, you can see that India and Japan are roughly the same size. CIS stands for the Commonwealth of Independent States, the former Soviet Union. And so really a lot of work needs to get done by these countries. And then finally, as a lead-in to our guests, in preparing for this episode, this really struck me as a really neat chart. And I thought it very ably and simply kind of explained, the problem and why this is such an interesting solution to go with plants. That if you're talking in the gigatons of 35, 40 for that energy-related CO2 emissions, there's also the natural sinks beyond that. And so while it may be true that human-released emissions are something like 5% of the total, it's a pretty high percentage of the problem. And so with that, let me turn it back to you, Maynard, and use that as a segue to our guests.
No, that's awesome, Colin. Thanks, everybody. And I agree, that chart was awesome. I can't wait. The team is going to give us a little presentation here from Salk, but being able to just talk about these numbers and what they are and get a sense of the scope of everything is great. I want to try to do the introduction justice because, again, as I mentioned in the beginning, we're just so crazy excited about this because this is not only innovative stuff and neat stuff and super sciencey stuff. It gives you a feel for the way things could work out in ways that none of us are even thinking about now, which is the kind of stuff we love. So let me first introduce the co-directors of the Salk Institute. It's their Harnessing Plants initiative. Dr. Wolfgang Busch, he's a professor in the Plant Molecular and Cellular Biology Laboratory. He's an associate professor at the University of California, San Diego. He's got a phenomenal academic background, PhD degrees in biology in Germany. He started at Salk in 2017. He did some work at Duke. He's published in 70 papers, and he's won quite a number of awards. And so welcome, Dr. Busch. We're so happy to have you, sir.
Thank you very much.
Let me introduce, I also want to introduce the other co-director, and you're going to hear from her first, I think, as they do a little presentation, Joanne Chori. So Dr. Chori is a graduate of Oberlin College. She did PhD work in microbiology at Illinois. She did her postdoc at Harvard Medical School. She went to Salk in '88. In 2003, she was named Scientific American's Research Leader in Agriculture, and she's a member of a number of esteemed bodies, including the National Academy of Sciences, and is a fellow of the American Association for the Advancement of Science. So welcome, Dr. Chori. We're so excited to have you with us.
Thank you, Maynard. It's nice to be here.
And then I've got an old friend of TPH I've got to say hello to, Dave Lawrence. Dave is the chairman of the advisory council at HPI, and he was a 30-year executive with Shell. He was an EVP in global exploration, investor relations, and in planning and strategy. He led Shell's wind energy business, worked in a number of areas around Shell. He's been a past director at Stone Energy Corporation. He's a chairman of the External Advisory Board of the Yale Climate and Energy Institute. He's a commissioner of the Aspen Institute Commission on the Arctic. He's a Wyoming man. And also, he is a geology instructor at Yavapai College in Arizona. He got his PhD in geology and geophysics from Yale in 1984. Dave, we don't have enough Yale energy guys in the world, and so we're delighted to get to hear from one today. And let's a couple more introductions, and then we'll get started. We've got Joel Knoll. Joe Knoll, he's a PhD. He's a professor and director with HPI. He holds the Arthur and Julie Woodrow Chair at the Salk Institute. The goal of the work is to understand the chemical, structural, and evolutionary tenets governing an extraordinary form of biodiversity and biocomplexity. This is where the stuff starts to get complicated, but this is also where it gets really fun. He's got a BS in natural sciences and chemistry from Pittsburgh at Johnstown, and a PhD in chemistry from Ohio State, go Buckeyes, and did his postdoc work at Yale, so we're heavy on the Eli's today. Great to have you, Joe. And last but certainly not least, Tony Stiegler. He's the Senior Director, Policy and Regulatory Affairs leader at HBI. He's got an extensive legal background, but particularly in the areas around life sciences, pharmaceuticals, drugs, all this new technology that's going to make the planet a better place, but that sometimes people disagree about. So let me just say welcome again. It's so exciting to have you guys. We'll attach a link for all of you about the Salk Institute, but this is obviously as in Jonas Salk and the cure for polio. And so the history of the organization and the science is legendary. And now they have turned their attention to one of the problems, bigger problems of our times. So I'm going to stop talking because nobody wants to hear me. Dr. Chori, why don't I turn it over to you? And I think you guys are going to start with a little walkthrough, and then we'll get to ask you some questions. So thanks, everybody, and welcome, Dr. Chori.
Okay, thank you very much for having us. And let me just get going here. So in 2017, we formed an initiative, and it was called the Harnessing Plants Initiative. And this was because of a challenge that we got from our president at the time, Elizabeth Blackburn. And so she came to our faculty. We have about 55 faculty at Salk, and she told us, we should be doing things bigger than our own lab. So the plant group took this very seriously. And if I can have the next slide. Okay, yeah. So in November of 2017, we launched this initiative, the Salk Harnessing Plants Initiative, and it has two aspects to it. The first one is a little more developed, so we'll talk about that for longer. And then the second one is being led by Joe Noel on coastal plant restoration. And I think you guys will be pretty interested in that. And he's thinking about how we can restore our wetlands for carbon sequestration. And so the program we're going to talk about first is called CROPS, for carbon renewal on a planetary scale. And in this program, we can go carbon negative. So this is actually really pretty powerful. And our approach is to use plants to do this, because we're plant biologists after all, and we thought about what photosynthesis does. So we're a carbon-based culture. And so what plants do is they suck CO2 out of the air. They're really good at that. And then they fix it with the power of photosynthesis and with the light energy into chemical energy that involves carbons. Okay, and so can I have the next slide, please? So here's our talk. If I can go back by one. Thank you. I'm going to just set up the problem, but I think it was already done well with the slide that I have. And then we'll tell you about our approach and the impact that our approach can have. Okay, so I'll have the next slide. I'm going to skip the executive summary and go to the next slide. Okay, so here's the problem. We already heard what it was. So the Earth's carbon cycle is out of balance. And this is the reason why. There's good news and bad news on this slide. The bad news is that, for every 746 gigatons of CO2 that's captured by nature, by photosynthetic biomes in the ocean and in all the land plants and et cetera, a lot of that gets released back in nature. So the carbon cycle is in balance when we do it that way. But with human input, we now have added 37 gigatons of CO2. We use CO2 in our calculations. And that we're releasing that every year right now. And so CO2 by the numbers saying, we're in 18 gigatons excess because the Earth can do about 20 of those that are released. So we think of plants go in the full cycle, right? And so plants live and then they die. And when they die and decompose, all the CO2 they fix goes back up into the atmosphere. So we have our vision. And so, all right, so let me tell you the good news and the bad news. So the bad news is the Earth is warming because of all that excess greenhouse gases up there like CO2. And the Earth warming is causing climate extremes, and we've all witnessed a lot of that. And everyone believes that's really coming, I think, now. And so that's the bad news. But the good news is that, plants like CO2 if they use it like it's, part of their diet, okay? And so because they like CO2, they'll suck it up for us. So maybe we can get them to help us handle what's going on. So we have a nature-based solution. And because we're plant geneticists, we thought about this in terms of genetic approaches. So what would be the traits that you would need to have in a plant that's going to sequester more carbon? Okay, so let me tell you the good news. The good news is that the capacity for plants to do this is there because every year, plants are sucking up 746 gigatons of CO2, right? And so we only need to get rid of 18 to put this emissions in, that the Earth can handle the whole carbon cycle again and put it back in balance. If I can have the next slide, please. So here's the role of plants. Plants have evolved over 450 million years, land plants. And so they're really good at sucking up CO2. So what they do is suck up CO2 and then they release it later when they die, right? And so we just think that all we have to do is get nature to be 2% more efficient at what it is already doing. And then we can get plants to store carbon in the soil for us. And this will mitigate the climate change. Okay, so that was our idea. And so let me show you how we're going to do it. If I have the next slide. So our vision is we want to harness the natural power of plants to rebalance our carbon cycle. So I like to think of plants as, they're kind of an Olympic level athletes, but they're not going to win the gold medal without some coaching from us. So we're going to tell them how to win the gold medal. And so if I can have the next slide, here's how they're going to do it. Okay. So we've trademarked as Salk ideal plants. So the normal plant, it's the annual, it sucks up CO2, fixes it into various carbon forms, and then releases it at the end of the growing season. Okay, so we think they're distributing some of those forms a little bit unequally. And so we want them to distribute the forms so that they're making more long-lived polymers, as opposed to a lot of the sugars they make, which is not long-lived, and so carbon wouldn't stay in the soil. And so that's one way to do this. So we're going to get the plant to deliver us more long-lived polymers. And then the second thing we're going to do is get plants with bigger roots. And we want those roots to be deeper because those deep roots are going to be down in an anaerobic environment and they won't decompose so fast there. Okay, next slide, please. Okay. So our ideal plants have deeper roots, they're more massive plant roots because we need to get as much carbon as we can stored down there. And they also are going to be making more recalcitrant carbon-rich polymers, which plants know how to make in their roots anyway. Okay, so I'm going to hand it over to Wolfgang now, and he's going to tell you how we actually did this or are doing it.
Okay, thanks, Dr. Torrey.
Glad to take it on. So Joanne told you about the fundamental idea, and that is to do a full cycle, to make plants go full cycle, to retain more carbon in the soil, because 40% or more than 40% of the dry mass of roots is carbon. So we want to, as Joanne outlined, find ways that the carbon will stick around for longer and put more of this carbon in the soil via the root structure itself. And so for this, so this is essentially an engineering approach, a bioengineering approach. So much like, you know, an engineer would have a blueprint, all plants, like all organisms, have a blueprint written in their DNA. And so the genes are the instructions for organisms to make stuff like roots. So we want to try to find the instruction codes in the genome, in the genes of the DNA, that allows plants to make more roots, deeper roots, and more of the suberin molecules that stays for longer in the soil. And so we got to find these genes. We got to decode all these three characteristics. And then once we have this, we have the instruction set that we can basically try to put into the crop plants that cover a lot of acreage. Because even if we will be successful, well, when we will be successful to coach the plants to store more carbon for longer, every plant has a small contribution. So it's all really about the acreage, right? So the soil bank, the soil carbon bank needs to be gigantic to have a global impact. But the good thing is there are a couple of crops, and I'll show you later, that cover an enormous amount of land. And so for these crops, we want to take these genes, this instruction sets, and put it into these crops via different methods, and then test, well, does it work, and how much of the carbon actually stays in the soil. And so how are we doing this? So that gets a little bit into the details, but I think it will be interesting. So we're doing something called genetic screens, and that's basically kind of like a reverse engineering kind of effort to identify these genes. And so we do this for all these three characteristics: deep rooting, more root mass, and suberin. And we're doing this in multiple different ways. We're doing this kind of like in a prototype model. The Arabidopsis thaliana plant, which is very familiar to all plant geneticists. There's a lot of resources that we can leverage for this to learn from this one system. But we are also doing it in these crop plants itself. So we are basically having two kind of independent approaches that will allow us to find a lot of different sets of instructions to make bigger roots, more roots, and more suberin. And then once we are certain that this works, we put that into the crops via gene editing, like very advanced methods, or using breeding, like something that people in the industry has been done for centuries or millennia even. So where we actually use like smart statistical methods to know exactly which plants to cross to reach that impact. All right, so once so just an example why we are actually very certain that we can do it. This is an example from the Salk science where we identified a gene, so a single kind of like set of instruction that when you change it, it leads to deeper rooting, and that's what you see here. On the left, you see one of these model plants, Arabidopsis. You see the roots in the soil outlined in red, and you see that Arabidopsis is actually a pretty shallow rooting plant. So when we change this gene, this set of instructions, with a like tiny change, we actually can direct the root system much deeper. And so we know we can do it. And so we also know that there are many other of these genes out there that we then can combine and reach the best effort, and just need to do the same change in the right genes in the crop plants. Another example that makes us very certain that we can do it, we can also do the same thing with root biomass. So here are two examples. On the left, that's the normal Arabidopsis in the left picture, and also in the right picture. And on the right in each picture is a slightly genetically altered and engineered variety of this. And you can also see by making precise, simple changes in the genetic codes, we can increase the root biomass significantly. So we know we can do it. And so right now we're actually running full speed to not only have one gene for each of these characteristics, but many genes, and so that we can actually make massive changes. The same, if you would go back, the same holds true for our suberin, this carbon-rich polymer. We call it the carbon storage device. You see on the right that the structure, what you need to know about this is that every little black dot is a carbon atom. So you can see that this molecule holds a lot of different carbon atoms, and it holds not very many oxygen atoms that are marked in red, and that makes it very stable. The structure itself, which is almost crystalline in the center, makes it very stable. And that's why we think, and in particular Joe Noel, who's always also on this call, thinks this is the reason why it's has so little decomposition in the soil. It's naturally occurring. We don't need to reinvent the crop plants. It occurs actually, it gets made by every plant root. So we just need to find ways to make more of it. We actually have identified multiple ways to do this. And so stay tuned in the next couple of months or years once we come out with this. So we know we can change all these three traits, these three characteristics that will lead to more carbon storage for longer. So then the next step is, now that we have these sets of genes, these sets of instructions for all these three characteristics that make plants store more carbon for longer in the soil, we're going to move to the crops. And so here is which crops we're actually working on. Those are mainly food crops, because that's what people grow, and also that's what we need as a growing global population. It is not a good idea, we think, to compete with food crops when you're looking to cover land, because we need trillions of more calories for the 10 billion people that will be on the planet by the end of the century. So we focus on crops that they can not only produce food, but also provide this additional service to us, which is carbon sequestration. And so we focus on wheat, corn, rice, soybean, sorghum, and canola. Each of these species has different pros and cons, and we are trying to figure out, and we are actually actively doing this, what's the best way to make each one of these crops with the genes that we know about more efficient for store more carbon for longer. Another set of crops is actually very interesting, is cover crops. So those generally don't cover as many acres, but their only function is to make the soil better. You don't need to worry about the yield in these crops. They're actually really one of their main functions is to put carbon and nutrients in the soil already, and we think we can make them better. So we're kind of like having a double strategy here to maximize carbon storage. And so this is, as I was saying, our rationale, why to grow for these major food crops. So if you think about the acreage that they occupy on the surface of our planet, it's massive. If you take together these green these green food crop species, and you add together the acreage, if you would pool them in a place on Earth, it's more than the subcontinent of India. So they would cover this enormous land mass. And so that's an enormous advantage, because you can actually get a very large drawdown effect if you make them better. And so more than 50% of the agricultural used land for growing food crops is covered by these handful of species. And so we can focus really on these big guns in the food production area. All right. So next slide, please. All right. So you might wonder how do we actually bring what we know? How do we use these genes, these sets of instructions? How do we bring these in these crops? And we actually have many different possibilities. And the best way actually depends really on the crop. So we have traditional breeding. People have done it for a long time. There have been major advances in breeding over the last couple of decades, over the last 20 years. We can actually use computer models to be way more efficient and much faster. You can even use gene editing, which is a precise change of a single genetic characteristic, and is indistinguishable from natural mutations that basically get into the breeding process usually. And then there's, of course, the possibility to use transgenic GMO if we are in a big hurry, and if this would be beneficial in terms of the crop that we are working on. So we have a lot of options, and we are following all this. The key then is to check out how do these changed characteristics actually relate to carbon storage. And for this, we have started to do something very unusual for Salk fundamental biologists, to go out in the field and actually plant all these plants in the field and measure how much more carbon for longer can we expect these three root characteristics in these species, in different soil types, how much carbon can be stored for longer, so they can inform more quantitative models. And we are working with soil scientists and have already started several field trial locations. And we began these in 2020, but we are actually accelerating and expanding this endeavor, which will be very important to get better numbers on this. All right, next slide, please. So what kind of impact could you expect? So when we started to decide whether we want to dedicate all our time and effort on this project, we thought, can we make a global impact? And so we made a simple thought experiment, and this is really a thought experiment. And the numbers, as I was saying, will be refined very much based on the field trials. But if you think you have a certain amount of carbon in each plant of each crop, you take into consideration the global acreage, and then you ask, if we were to make the plants store a certain amount of percentage of their carbon, and that's in the left, that's basically given in the rows, how much of the surplus CO2 per year can we draw down? And of course, that depends on the acreage, which is given in the columns. And so basically, we thought, let's focus on the crops that we are working on and how much they can actually sequester if we assume different numbers for each of these different axes, the acreage converted and the amount of carbon sequestered. And we can actually get easily, or well, not easily, but it's reasonable to assume that we can get to 4 gigatons to 8 gigatons of additional CO2 sequestered per year, which is an enormous amount of the surplus CO2 that globally gets emitted. All right, and so so why would anyone, apart from getting, hopefully, getting carbon credits, but if there wouldn't be carbon credits, why would people be interested in actually doing this anyway, even without carbon sequestration? This is because all these characteristics that we are working on that lead to more carbon sequestration are good for the soil. More carbon gets in the soil. Storage carbon is good for productivity and stress resilience. Given the effects of global climate change with increasing flooding or terminal droughts, that might actually be, or that will be, characteristics that will be highly desired anyway. And so we think that we actually can provide a solution in which these plants can provide more calories to a growing population compared to non-stress resilient plants, but at the same time provide this additional effect of carbon sequestration, which we really urgently need. All right, and with that, you can advance the slide, and I'm going to give it to Joe Noel for the second part of our project.
Thanks, Wolfgang. Everybody hear me? So I'm going to talk about another ecosystem, a little bit different than crops, obviously, and these are wetlands. It's called the Salk Coastal Plant Restoration Program, but it also involves not only coastal waterways, but inland. So we're really thinking about what we would call the salinity gradient. So from fresh all the way to fully marine water. And I'll give you a very, very brief history of why my lab became interested in wetlands. And that really has to do with this substance that Wolfgang has mentioned called suberin. As we were thinking about suberin in my group, now it's about 7 years ago, we were looking for plants that actually made more of this substance, which the common name would be cork. And of course, cork oak produces a lot of it. But what kept coming up increasingly were plants that live with their feet wet. And so the suberization of the roots, which is one of the 3 characteristics that the harnessing plants group is focused on is what we think is a favorable trait. These became interesting because they potentially could instruct us as to how plants over evolution have already evolved the ability to make more suberin in the root systems. But as we obviously learn more about these systems, we found out increasingly that wetlands store an incredible amount of carbon. They directly intersect in many ways with the energy sector. But unfortunately, at a molecular level, genetic level, they've really been poorly understood. And so that opened up a possibility for us to look at wetlands. Next slide. So as I said, these are systems where plants either seasonally or throughout an entire annual season live either partially or fully submerged in the water. They currently occupy about 10,000 square kilometers. If you convert that to hectares, that's about 1 billion hectares worldwide. So that's compared to our arable land with crops, which is about 1.6 billion. It's just slightly lower than that. So about 7% of the Earth's surface. They draw down an incredible amount of carbon dioxide every year and convert it into molecules that, because of their unique environment where they live in a rather oxygen deprived or oxygen eliminated zone, can store carbon rather than for years or decades, can store carbon for centuries in their sediments. And in fact, there's very good fossil evidence. We had a slide, I took it out, but one of my favorite periods or epochs or eras of the Earth was the Pennsylvanian, where wetlands actually are presumed to have given rise to a large fraction of our fossil fuels, particularly coal. I'm also drawn to it because I grew up in Pennsylvania in a coal mining family. But the wetlands are a major contributor to that. And in fact, it's thought that suberin and another polymer that my lab has worked on, lignin, which is actually wood, were the two major innovations in the early Earth that gave rise to their ability to resist decomposition and the formation of fossil fuels. Now, unfortunately for wetlands, they've been under significant developmental pressure for a number of centuries. In fact, you could estimate that 60 to 70% of wetlands have been lost since the 1900s. That loss is still increasing, less so from development, but more because of increasing melting of the tundra and rising sea levels. They're also being lost. And that actually brings up a potentially very major issue for greenhouse gases, because they store so much carbon and they store it for such long periods of time, centuries to millennia. When you lose them, in particular, wetlands have been lost most commonly through agricultural development. That centuries to millennia old carbon that's been stored becomes rapidly assimilated and exposed to air, and then is emitted both as methane and CO2 into the atmosphere. So not only do you lose the ability to sequester carbon, but you now contribute an immense amount of very old carbon back into the atmosphere. And we see this most acutely in the thawing of the permafrost in the tundra parts of the globe. Next slide. So what we at Salk have been really focused on with the plant group at a chemical, biochemical, and genetic level is really understanding at a molecular level how plants encode all this information, that they do all these miraculous things, in particular sitting at the base of the global carbon-based fuel food chain, where they use CO2 to make a whole myriad of molecules, as Wolfgang and Joanne very nicely presented. And as I alluded to, the issue in wetland environments, these are plants that are incredibly important from an environmental and increasingly a climate mitigation strategy for the future of our planet, but they really have not been studied at a molecular level, at the level of the genomes and the biochemistry that they use to adapt and survive in these very challenging ecosystems. And so we've been collecting various primary producers in wetlands, both fresh, brackish, and marine systems, mainly in the United States, and have begun interrogating their genomes. So basically, we would like to read out the rule notebook for how they actually carry out the chemistry and the biochemistry that they do in these very challenging ecosystems. Next slide. This is just an example. We have a very active collaboration with a number of scientists that span a number of different disciplines in the Mississippi River Delta region in and around New Orleans. And this is just an example of what the Delta, for instance, which actually does span the salinity gradient from fresh to fully marine environments, stores in terms of the carbon burial in its sediments that's both locally derived from the plant matter, the flora and fauna that live around these areas, but also distally from sedimentation down the Mississippi River and its tributaries, as well as the tidal flows into the Delta. So we think that this is a wonderful experimental test system to really understand how the genomes and biochemistry of these plant systems really intersect with their ability to capture, store carbon for long periods of time. Next slide. And so I'll just sum up, just giving you some characteristics of what wetlands actually do. If you look at them at a per unit area, they can store 30 to 100 times more carbon than land plants. So if you compare the 10 billion hectares of wetlands globally, that's a significant potential contribution to our carbon drawdown ability. As I alluded to, they're naturally very abundant in some of the same characteristics that we would like to engineer or select for in crops, including root suberand, so that their genomes and their biochemistry really do inform us as to how one would adapt food crops and cover crops to more recalcitrant forms of carbon-based molecules. They are threatened by invasive species, so we think that understanding genomes and that intersect with ecologies will help us to understand invasive speciesness. They're very efficient at stabilizing and rebuilding land. One in progress set of studies we've done is on cattails, which I'm sure you're all very familiar with. It's the wetland grass that has that hot dog looking brown seed head on the top. They're incredibly effective at sedimenting water columns, which are carbon laden, and rebuilding land. But economically, they're also important for fisheries. And then finally, they have a direct intersection, for instance, with agriculture, because they do a tremendous job in cleaning our water, both in terms of over nutrification, but also in sedimentation and bioremediation. So we think that, looking at these systems at a molecular level is another shot on goal for really understanding how plants and plant-based carbon sequestration can aid in mitigating CO2 emissions and methane emissions. Okay, next slide. I think that's it.
Thanks, Joe. I just want to talk about the impact of the kind of the science that you've seen and what it will mean towards addressing the climate challenge and specifically carbon offset technologies. We think that the Salk technologies are the most credible, the most scalable, and the most sustainable carbon offset technologies. There's a number of reasons we think that. First, let's begin with scale. You heard Wolfgang talk about 4 to 8 gigatons of scale per annum. Joe talks about similar scales, multi-gigaton scale for sequestration in our wetland systems. Removing a gigaton of CO2 is no small effort. We always have to remember that. We need to be removing about 20 gigatons per year just to meet the 2-degree C scenario. What does it take to remove 1 gigaton a year if we think of other systems? That's about equal to 250 coal-fired power plants. It'd be equal to about more than 250,000 wind turbines. Or it'd be the equivalent of removing about 200 plus million vehicles from the road. So each gigaton is a big deal. This doesn't require any new planting or harvesting techniques, and it builds on our existing global systems. It can be deployed across the globe. It doesn't need to be specific to the US, to North America. Significant opportunities in Latin America, in Asia, across the globe. It's very cost effective. I'll talk about this briefly in the next slide. But if you think about some of the large scale deployment models that we have for other technologies, they are significantly more than our aspiration of less than $10 per metric ton, less than $10 per metric ton. It's an iterative approach. We have built-in feedback loops for learning, as we do in much of the technology we do in energy, to take the learning from our crops, feed it back to the science, and improve the crops to further sequester more carbon and improve our plants. And it's timely. We're moving on a fast pace, and we'll be in a position to prove principle at the megaton scale in the next 5 years, and then into that multi-gigaton scale as we move into the 2030s. Let's go to the next slide. I just want to show, this is a slide. The y-axis is a measure of cost efficiency for this carbon sequestration. Being at the top of the chart is good. You sequester more tons of carbon per dollar spent, and the x-axis is just the pace at which you're able to deliver that carbon sequestration, from slower to faster. The size of the bubble is the annual amount of CO2 reduction potential in gigatons, and that gray bubble on the end is about 3 gigatons. So what we're looking at with Salk ideal plants is something that's both fast, it's massive, stores multi-gigatons of CO2, and it's cost efficient at less than $10 per ton CO2. And you can compare that to some other techniques in the lower left. Renewables can store a massive amount of CO2, but typically at a higher pace. And the pace of renewables in the overall primary energy supply will take significantly longer. We talked earlier in the session today about different carbon capture and direct air capture techniques, weathering techniques. Those will be smaller amounts and more expensive, and so forth. Forestation is another good thing, but at a lesser extent than this. So why do we like this? Very large scale. We can do it very fast, and it's cost efficient. Let's go to the next one. What's the time frame that we're on right now? I'm very fortunate to be working with this team in the phase 1 science development, and you're hearing about all the great science that's being done, and more to come. Very, very exciting stuff. We want to move that into the part of this that I'm involved, which is in phase 2, and to getting into building this at scale. So moving into field trials, increasing, testing our multiple shots on goal, and increasing our presence, and then moving into initial commercialization. We hope to get to 1 megaton additional carbon sequestered proof of principle by 2027. And then as we move into the 2030s, and the way we're work at multi-gigaton additional potential. And we're happy to talk in questions about how we might be able to get there. So with that, I will open it up, I think, and hand it back to you, Maynard, and we'd love to answer any questions you might have.
Well, that sounds great, Dave. And so, thank you, Wolfgang. Thank you, Joanne. Thank you, Joe. Thanks, Dave. That was a fantastic presentation. Maybe one place to start, which was really neat, is you guys talked about something that doesn't get talked about enough, which is, how quickly can we do it, and what's the cost to capture the CO2? And so, Dave, your slide was really compelling. It had a lot of neat stuff on there. Do you mind just sharing some of the analytical history of how you put that together and studied that? Because I think that it showed your oil and gas background was coming out there, Dave. You were doing like finding cost for a ton of CO2. Tell us some more about that chart. That was a fascinating one.
A little bit of unit finding cost, Maynard. So that was the approach we were trying to use. But I think if we put the chart together, what we've looked at is the potential for carbon additionality in both crops and wetlands. And we've looked at the amount of acreage that we need to be able to capture this. And we've said we'd need to get this amount of crops capturing this amount of additional carbon on this amount of additional acreage by this amount of time to be able to get us to a gigaton scale. And that's why we have our multi-gigaton scaling opportunity in the 2030 plus time frame. But we've also looked at, and looked very carefully, we just want to start, have to start with something, and we'd like to start with a megaton. So we think that if we can do that, and when we can get on hundreds of thousands of crop acreage, plus wetland acreage, that we should be able to do that by 2027. Now, why is this so cost effective in general? The reason is because you are not having to do a number of things that you have to do in other carbon sequestration technologies. We're not having to build major new infrastructure. We're not having to acquire major amounts of new land. We're planting seeds that are going to be planted anyway on that sand, but these seeds and the plants they produce will have deeper roots, more massive roots, and more carbon. And that planting of those seeds is something that's already done. So the additional cost is very minimal. And when we look at that, Maynard, what I find so exciting is that we think that we have the potential, and I'm sure there'll be a learning curve, but we have the potential to be at less than $10 per ton. And that would be a true breakthrough in the world of carbon sequestration, especially as you look at things which have much higher costs, like direct air capture, as we know, which can be north of $100 per ton up to $300 per ton as we do that. And biomass and mineralization, for example, can be in the $50 to $150 per ton. So we think we're in a pretty good sweet spot, to use another term, that would be, I think, really right for addressing carbon change, climate change.
So, Joe, one question for you. You had the stat about the amount of wetlands we've lost since 1900, and you just talked about that. I think, I don't know if this is something you can estimate for us, anyone on the team, but I think we hear a lot about the loss of the planet's vegetation, like we had this many trees, now we have this many, and then you made the wetlands comment, but sometimes you hear that the increased CO2 in the environment has actually caused, now we have a lot of new growth. Can you just help our viewers, like what is the sort of the mark to market on how much we're up versus how much we're down? Like, have we still destroyed a lot more than we've added, or what's the net balance, if you will?
Yeah, I'm not sure I'm qualified to comment on markets, but certainly it depends on the kind of photosynthesis plants do in terms of their CO2 drawdown and how much that it adds to biomass. There's actually a couple studies, some very recent, that have come out where rapid growth of biomass due to increased CO2 results in biomass that is a lot less recalcitrant, right? So that it's biomass that is relatively labile in terms of its yearly turnover through decomposition. So, we don't know at this point, but certainly whether that increased CO2 is going to contribute to more recalcitrant or refractory biomass, I think, is an open question. In terms of wetlands, I think it's still a net negative because you're still losing them at a very appreciable rate due to sea level rise. The land is actually sinking. In the Delta in particular, we face both extremely. And so you end up losing the ability to grow more vegetation in those areas.
So, Joe, I'll hazard a guess at what I think you said. More CO2 could be creating more plant life, but it may be creating plant life that doesn't absorb as much CO2 because it tends to die quicker. I think that's what you said.
Yeah, so effectively, I mean, it absorbs a lot of CO2, but it then dies quickly and decomposes. So you see this quite a bit in the oceans, where you have these large algal blooms like diatoms, et cetera, mainly from high nutrients, but it gets turned over incredibly quickly. So very little of that is actually stored CO2. I don't know if my colleagues might want to comment on that as well. But.
I'd just add to it. I think the great advantage of wetlands is first to stop them. What needs to be done is to stop destroying them, because it releases so much greenhouse gases into the atmosphere. This technology that we're talking about here can stop the destruction of them, and then to preserve what we have is another thing, that the plants that we can grow can help preserve those wetlands. And then the third thing is we can actually build new wetlands. And the building of new wetlands by trapping soils with these plants is extremely effective at carbon additionality, and is probably one of the more cost-effective ways that you can really trap very large amounts of carbon.
Yeah, picking up on that last point, I just want to applaud the team for just being so reasonable and sensible. And we're just really impressed that instead of focusing on changing human behavior 100% in something that won't work and is totally unrealistic, that you're reminding us that we have now the technological skill as a species. I love the way Joanne put it, to help nature be 2% more efficient. And helping nature be 2% more efficient is way more important than some of the things that people put out there without really knowing the numbers. And on that point, the numbers, in some of your literature, you talk about the auditing systems that you envision, how you'll be able to just be very dispassionate and empirical in tracking how much carbon does in fact get sequestered. Could you talk a little bit about that, Wolfgang, or anybody else who feels moved to do so?
So I think tracking is really important, right? We are thinking about plants. Plants are kind of the investors in the soil carbon bank to store carbon for longer. So that's kind of the idea, and we need to assess and track carefully to see how much carbon every year gets deposited, and how much of this goes out, or how much doesn't go out, right? And so that's the additionality over time that we're talking about, and that will be really important. And so this is complicated. Nature is complicated. So what we know is that we actually have to get these numbers, in 4 different crops, in different soil types, to basically have a good assessment, so that farmers, and the industry can actually, run the numbers, make the case for it. And there are various methods, proposed for this. Dave and Tony basically, are following this very closely. Whether or not, you should measure it by seed, for instance, say you have a variety that stores that much carbon, or whether there is like a measurement approach in the field. For establishing the numbers, we need to measure and track a lot. Whether or not you need to do this every year if you're a farmer, I think that is a very good question that I think Dave or Tony can maybe answer what the current debate is.
I think you have two scales of things that we will be demonstrating. One is, again, familiar with, I try to throw in these geologic terms into this biology. One of these is in the provenance of that carbon. So does that come, we need to be able to demonstrate that the carbon in the soil comes from the plants that we plant, and that more of it stays because of the plants that we've planted. That's some fundamental science that we're working on using different laboratory and measurement techniques. When we show that proof, which we will, then we need to be able to show that we can measure that total additional carbon at scale, and be able to do that efficiently. That's a broader scale problem that will be done with others. That process, and again, Tony can talk about this, needs to be part of the protocols that are used for carbon additionality, and that can be done efficiently and cost effectively, because the measurement system cannot cost more than the abatement of the CO2 that you're doing. So we're working on that, but Tony, do you want to just take that?
Sure, Colin, a great question, and I'll amplify one point. There's a great development today. We think that The Senate Ag Committee's Growing Climate Solutions Act will be released again today. This is version 2. One of the big changes is that the USDA would be put in charge of creating a program to certify the carbon credit verification services and the technical assistance providers that are required for MRV, measurement, reporting, and verification. So this will take, as Dave said, some standardization of protocols. The USDA is in a great position to help lead that. So we're excited about the progress forward.
I just have one comment I want to make to Colin, who called us rational because we've been called totally crazy and audacious, for bringing up these kinds of ideas. So it was nice to hear that someone thinks we're rational, because we think we've been thinking about it a lot,
I think you're more than rational. I think this is genius. It's
Okay.
really, really cool.
Just as a follow-up question on that comment, we're talking a lot about carbon tax credits that potentially could be in place on the policy side. I was wondering if you could speak to, I guess, just policy in general around this type of technology. Are there any economic incentives that could be on the horizon that could get investors or the industry interested in participating as this technology evolves? And then I guess just dovetailing into that, what's the industry's response so far around this technology and potentially using this in food crops as we move forward?
You bet. So maybe I'll take the first.
Take the first, and I'll take the second part.
Perfect. So from a policy perspective, we've had great interest from many on the Hill. And we think that, as Wolfgang mentioned, there are these secondary benefits associated with additional carbon in the soil for food security. So the farming community is very interested in that. There's great interest from organizations like American Farmland Trust to ensure that the farmers are rewarded for their land stewardship practices. Likewise, on the commercial side, we've had tremendous interest from a broad array of potential partners, talking to all of the big commercial ag companies and seed companies who will ultimately be necessary to help us distribute the technology and educate farmers about uptake. So as Dave mentioned, and this is where I'll pass it off, the economics are extremely attractive. And if we can figure out a model where the farmers are able to make a fair return, there's economic incentives for those who are in the supply chain. We think that there's a great opportunity for rapid uptake. Dave?
Yeah, thanks. This is no small challenge, and we recognize that, and we're in the early stages, but as we're getting right in that practical scaling stage. So our first task is again to get the science proven up and then move into this scaling stage. So we recognize that as we do that, there are going to be different business models, and there'll be different business models and scaling models that we can apply for different crops. They each have their own particular parameters. So we're building those models. We're not doing this in a vacuum. We are talking to everybody from the end user on the net zero side of that ever expanding list of net zero commitments in the market that will create, to the intermediaries, to the major ag companies and seed companies, and then towards the farmers on the front end. That landscape of the value chain, I think, will determine the ultimate business models that we choose for each plant. But our vision really, and I really, this is all from the PIs that you see here, is really to get this to a gigaton scale. And that's our driver as we look at everything that we do. What will be the most efficient and rapid, scalable way to get this to this gigaton scale, whether it be in wetlands or whether it's in crops?
Matt, one other point on that, there's great bipartisan support. So this is a solution that folks from both sides of the aisle are equally excited about. So that makes us very excited as well.
By the way, these business model type stuff is not taking forever. We'll be through this process. Well, you'll probably never be through it, but we'll be at a good stage in this process within a few months.
So maybe we've got to wrap up. It's really hard to let you guys go because this is about as much fun as it gets in the energy transition discussion. Wolfgang, you said one thing about you guys, had obviously focused on being able to do this in food crops, so that the solution didn't have to displace land that was being used to produce food because we've got a lot of people to feed and we got more coming. I thought it was just a great and fascinating comment. Are you thinking ahead about the potential for any plants that could be used to do this in much tougher environments? And part of the reason why I ask is every time all of us go to Midland and you're driving along, looking at usually not green land, you wonder about turning West Texas into a huge carbon sink using your amazing plants and maybe some recycled frack water or something like that. But is there anything about growing plants in harder to grow environments? Is that anything on your horizon?
Absolutely. So maybe we take a step back. So all land plants have roots, right? So these design principles that we're working on, deeper roots, more suberin, should be applicable to almost all plant species. And some of the plant species, of course, we could consider, tailoring it to marginal lands. We actually had a couple of years back, we were debating lively about, should we maybe focus on doing this on marginal lands, focus on some species, like switchgrass or some legumes that could be planted there. And I think it's a great idea. But when we ran the numbers in terms of acreage and thought about the system that needs to be in place to basically plant, millions of hectares of land, it seems to be much more, easy. It's still an audacious task, but the infrastructure is there for agriculture. However, we would definitely hope we inspire, many others who then can use the same design principles, maybe the same mechanisms to make a lot of other plants better. So, as long as there's somebody working on this, and as long as there's an economy that will basically provide incentives to the stakeholders to plant, West Texas with the super grass that stores a lot of carbon, that would be wonderful. And I think actually, we would hope that many more will be on board to focus on different plant species that then can be applied in very different environments.
We like early wins, though, Maynard. If you can get an early win in a major demonstration in hundreds of thousands of acres around Midland, that's not a bad thing.
Well, we'll call it the Salk Institute's TPH Farms experiment, and we'll go out there and green it up. I'm probably going to hear from some buddies saying, "Hey, what are you talking about, Brown? It's beautiful out here." But well, maybe Dave, I could throw this to you or anyone on the team as we wrap up. I mean, this has been, I mentioned up front, we have been looking forward to this so much, and you guys we had high expectations, and it's even better than we thought. How can we help you, whether us, the community of energy people and technology people who are watching this? How can all of us help you do what you're doing and be supportive? Because we're all really excited about this. To Joe's point, this shot on goal that you guys are taking here, it's fantastic.
I'm going to start, but then I'd love the team to come in. I think that to be generally supportive of these nature-based solutions as they're being discussed and approached, and the policies and the protocols around them are important. That's important work that's happening now in Washington and elsewhere, and it needs to continue. It needs to be argued, if you will, as part of the solution, and a very important part of the solution. So we'd encourage others as they look for solutions to carbon sequestration and managing carbon emissions, to consider these nature-based solutions, and certainly consider what Harnessing Plants initiative is doing as a critical component of that. But I would just tell you this, Maynard. I got into this initially. I'd spent most of my life working on the source side of this equation. And when I heard about this, I thought I might start working on the other side of the equation. So consider the sinks in addition to the sources. And I think if we start doing that, we're going to be able to rapidly come up with some really better solutions. But let me turn it to it's the team that inspired me. So let me turn it to the team for ideas.
I'll quickly chime in. One, two practical things that we need in the short term to prove principle in the next 3 to 5 years for these shots on goal are soil carbon sequestration field trials. We need the data, and soil health demonstration trials. So the principal investigators, the scientists on this call, are developing the seeds that will go in the ground. We need to get them in the soil. We need to develop the data, and we'll prove the early wins, and then it will have a chance to scale.
Fantastic.
So that means we need money. So if you have that, we'll take it. No.
Joanne, thank you for cutting to the point. We need some money. Yeah.
Because right now, everybody can't help set the standard. We have to find the right people to set the standard for the price of carbon that the farmers are going to be fixing on their particular farm. And so I think not everybody can help out and do that. I get asked that question a lot. What can we do to help? And I think, well, you can make a donation to the Salk at our website. That's one thing that's easy. But that doesn't necessarily get us there. But anyways, I think the other thing you can do is give up one activity that you're not really in love with, that you do in your life right now, like washing dishes or something, and then take that time and think about this whole problem, and so maybe you can come up with some other ideas of your own. But I think everybody has to get on board. Someone said that early in this call. It's a global problem, and global problems need global solutions, and that involves a lot of little global villages, right? So even if you're just helping out your little hometown, to get on board and be ready for all the bad weather and chaos that's going to come or whatever, because I don't think we're going to meet the Paris Agreement, right? And so we're going to be at least 2 degrees warmer, and according to our colleagues at SIO, Scripps Institute of Oceanography, that means chaos. So we'll see.
Well, maybe that's a great place to wrap up, because I think the punchline is no donations will be turned down. But I also it takes a planet. We all got to be thinking about this, and we just echo what Colin already said. We salute you guys. We're totally excited. We want to help. Please call on us anytime, and thank you for showing us some really rational, outside the box thinking, and we love it. So thanks so much.
Thank you.
Thank you very much.
I really appreciate the opportunity. Thanks.
It was a pleasure.
Thank you, guys.